Okay, so hello, Hafude, and aloha once again. Thank you all for joining us again today. Welcome to the 5th webinar in the Pacific Desk webinar series this fall. I'm David Hitzel. I'm the Pacific Desk Guam instructor. Today's topic of discussion is emerging satellite techniques. So once again, this is being recorded for educational and documentational purposes and will be posted simultaneously on Facebook Live, or should be right now. Please leave any questions or comments in the comment section and include your location and affiliation when you do that. And you can also ask questions through Facebook Live, and Ginger, I hope, will pass those over to me. And then there'll be a period, brief period of oral questioning at the end of the talks if you would like to ask a question that way. But otherwise refrain from using your video or audio while the speakers are giving their talks. And then lastly, the video recordings will be saved to view later on our Facebook page and will be posted after that on YouTube. And the link where you can find those are on our website. So on our website front page, there's a menu link at the top that says Pacific Desk Webinars. So if you click on that, it'll take you to a page that has a recap on all the webinars we've done so far and all the links to the previous videos. Okay, so some comments on the future of the Pacific Desk webinar series. So far, the webinar series has been well received. And since the introduction of the COVID vaccine, looks like it's pretty soon, maybe in the next month, but life will probably continue this way through at least the next spring. I think we'll plan on continuing these. I've got some ideas for a couple future ones, some more satellite products, maybe wave modeling, disaster management, things like that. But if you are somebody else who would like to give a talk, please get in contact with me, and we'd happy to give you time to present. Also for December, I'd still like to put together 1 or 2 office virtual tours for the Pacific Desk offices in South Pacific or in Micronesia. So if you would like to do that, especially if you're a past Pacific Desk level 2 student, you already have an introduction prepared, so you can just use that as part of your presentation. So it shouldn't be too difficult. So if you're interested in doing that, please contact me as well. So today we've got 2 experts in the field of satellite meteorology. The first is Roger Edson, who has been the Science and Operations Officer at WFO Guam since 2005. He's responsible for overseeing the training program of the National Weather Service Weather Forecast Office staff on Guam and incorporating new technologies into the WFO programs. He serves also as the Principal Scientific Advisor to the forecast staff. From 1998 through 2005, he was a research scientist at Antion Corporation, where he created trainings in remote sensing systems for Navy Typhoon forecasters, particularly relating to the latest microwave meteorological sensors. So some of his procedures developed during that time now reside within most of the world's tropical cyclone forecasting centers. And then from 78 to 98, he worked as a weather officer for the United States Air Force and retired as a major. He has a Master's of Science in Atmospheric Science from Colorado State and has prepared numerous technical reports, conference proceedings, and 2 referred papers on the subjects of microwave imagery and tropical cyclones. So our second speaker today is Moeka Yamaji, and she's a researcher from the Earth Observation Research Center in the Japan Aerospace Exploration Agency. So that's JAXA, which is equivalent to our NASA in the United States. She's been working there for 5 years, and particularly on the global satellite mapping of precipitation product, the GSMAP. She's in charge of the development of GSMAP applications, especially for the Pacific region, and has visited many of the Pacific Islands. Moeka has published 2 papers relating to dual-frequency precipitation radar, and a couple others related to aerosol optical depth. And she is on her way to finishing her doctoral research and submitting her dissertation in March. Okay, so one thing I wanted to start off with here is maybe somebody can comment in the comment section, or they can do it over the microphone. Does anybody know what this picture is on the left?
Probably the first Tyros picture of a hurricane.
Okay, good, close. So the picture on the right is the first picture of a hurricane. So Hurricane Esther in September of 1961, the first satellite picture. And the picture on the left is also from the same satellite in April of 1960, and that's the first weather satellite picture altogether. So both of those came from this little humble satellite over here on the bottom right-hand side of the slide. So these were taken 400 miles from Earth. And I think they illustrate how far we've come, but also illustrate some common themes still relevant today. So when we have a satellite picture, how much can we see? How well can we see it? And how often can we see it? And what exactly is going on underneath those clouds? This is a similar picture from 5 years later from Tyros 9, which was considered the first operational weather satellite. And this is a global mosaic of those images. So these original satellites were about 400 miles from Earth. So they're taking sort of pictures like a modern day polar orbiter. So they you had to put a bunch of pictures together to see the whole thing. So in Pacific Desk training in level 1, we introduce our students first to the concept of why satellite is so important for forecasters in their region. And that's due primarily to what we call the data void. So out in the Pacific region, there's just no land to have many land stations, and there's not many places to launch weather balloons or have rain gauge networks. So satellite images become sort of the bread and butter of tropical island forecasting. The next thing we do is we introduce them to the concepts of the types of satellites and the types of sensors. So the two primary types of satellites are the geostationary and the polar orbiters. The geostationary satellites, of course, are east-west moving, and they give a hemispheric view of the Earth because they're up at a specific height that allows them to rotate synchronously with the Earth. The polar orbiters, on the other hand, are much closer to Earth, and they go north-south around the poles. And because they're closer, they get much better resolution spatially, but they have poor temporal resolution. Both these types of satellites have sensors, and primarily the geostationary have passive sensors. So passive sensors receive radiation in the form of visible, infrared, or microwaves, which are emitted naturally by the Earth atmosphere system. Active sensors, on the other hand, send out a pulse of energy, typically microwave energy, and receive the reflected radiation. So the sensors aboard the satellites register radiation in the wavelengths between the microwaves and the visible portion of the electromagnetic spectrum. So in our traditional geo or satellites, we typically have passive sensors. And those passive sensors provide various methods for identifying clouds, deep convection, and estimating the life cycle of clouds on a large scale. So the visible channel allows us clear viewing of most of the clouds in the atmosphere, indicating their texture and definition. The IR provides a 24-hour view of cloud temperature, from which we can infer cloud top height. IR also allows differentiation of convective clouds from non-convective clouds. And then lastly, the water vapor emits radiation well at the 6.7 micrometer wavelength of the IR portion of the spectrum. So this allows us to identify motion such as upper level troughs at high and mid levels of the atmosphere. And then we introduce the students next to microwave satellite sensors, which can be both active and passive. They can be passive because the Earth system radiates some microwaves on its own, particularly from water. So unlike the visible and IR radiation, microwave radiation can penetrate clouds, allowing microwave sensors to see through clouds and water vapor. The scatterometry provides accurate estimation of surface winds over the ocean and can do so beneath heavy clouds. This is particularly important for determining the correct center or fix of tropical cyclones when performing the Dvorak method. Microwaves can also be used to estimate rainfall, particularly for large-scale climatology. The Tropical Rainfall Measurement Mission is an example of this type of satellite precipitation radar. Microwave energy also allows us, since we can see through clouds, we can virtually see into clouds as well. Because liquid water and ice emit microwave energy at different wavelengths, we can identify moisture at the levels of the atmosphere and therefore intuit some of the vertical structure of the storms. For instance, we can identify the location of rain bands and the relative convective vigor and water loading within tropical cyclones. So in conjunction with scatterometry, these 85 gigahertz and 37 gigahertz microwave channels can help us identify the center or fix of a tropical cyclone. And then in level 2, we introduced the students to the Himawari and GOES multi-spectral satellite products. So these products use the same visible and IR portions of the spectrum, but they're broken up into 16 bands or wavelengths, and they're typically at a higher resolution. So that there are now 3 bands for the visible, 3 for the near IR, and 10 for the IR portion, including 3 water vapor channels. Each of these bands has certain strengths in terms of what it can identify in the atmosphere and at certain heights. And the bands can be dyed in colors of red, green, and blue used by your computer monitor and then overlaid on one another to further help identify various atmospheric features. For example, convective clouds, aerosols, ozone, and surface features such as snow and fire. So this is an example of your one of your Himawari products, the daytime convection product. So this combines or subtracts bands and then dyes them in red, green, and blue. And then overlaying those bands on one another allows us to see specific cloud features. This technique provides a pseudo three-dimensionality to the satellite images so we can make more accurate inferences about the presence of convection, the stage in the life cycle of that convection, and which phase of water we are looking at within those clouds. These new Himawari products, however, suffer from some of the limitations of traditional geostationary imagery in that if they include a visible band, they're only available during the daytime. Okay, so from this brief sort of look at the history of satellite imagery and what's been available so far, it seems that there are 2 paths at the frontier of satellite technology. One is toward ever increasing resolution. And then the second one would be the wedding of the 3-dimensionality and high resolution aspects of polar orbiters to the large full coverage, real-time, high temporal quality of geostationary satellites. So our first speaker today is going to show us how things are going along the first path, and our second speaker today looks at how things are progressing on the second path. But looking back to the TIROS satellite, I think we're still after, the question is what's happening underneath those clouds? Is it raining? How much is it raining? And how windy is it really? Okay, so with that, I would like to turn it over to Roger.
Okay. Host disabled participant screening share.
Okay. Let me help you out with that.
Tell me when to click again. Oh. Still says that.
I gotta let it go here.
That seems like something happened. Oh. Still trying to get access.
Okay, There you go, Roger.
There. Let's see if I could get that one. Can you see my screen?
Yes, very well.
Okay. Do you see the pointer too?
Yep, I do. Yep.
The mouse?
Mm-hmm.
Okay, then I think we're ready to go. I stole your picture on Gani.
That's fine. I stole it too. I'm not saying where from, but I stole it too.
Oh, okay. I also noticed several of my other pictures in your intro, so I guess we share alike. So yeah, I didn't exactly know what group is going to be listening to this. So some of this is going to be repeated. Others will try to expand on what we were looking at before. So welcome, and I'll see if I could explain what we're going to be doing. We've already heard a little bit about microwave data, so I just want to, I'll be mostly explaining the different types and maybe how they work. And I might have some case studies to show at the end, but we'll just go through, and if people have some questions, they're welcome to kind of stop me and ask rather than me just keep drawing on in the unknown. And we talked about this. Why do we need microwave? Obviously, this is a microwave 85 gigahertz image, and we could see the rain bands. We also can see wind distribution from a scatterometer, and it's best even if you could overlay it with another image so that you could get that kind of three-dimensional feeling. This is from one of the new scatterometer types, and we'll explain that shortly. And then there's the new SAR type data, which isn't really that new as I started to read about it, but it is new for how we're using it for typhoon viewing. In this case, tropical cyclone moving into the end of the African coast, where winds are detected up in near the 120 knot. If you just double the meters per second, you'll get an idea. That's a lot stronger than we've seen, stronger than we get from scatterometer, and it helps to verify the other types of techniques we use, which is mostly the Dvorak technique. So microwave sees through clouds, as we talked about. It helps you get a position earlier. That position is extremely important. We saw it from the 37 gigahertz banding, because if you find the start positions at the beginning, you could do the Dvorak techniques, which is how they do intensity, and you could set up your models to better predict where the tropical cyclones are going to go afterwards. It's related to the rain bands, and I notice there's still people trying to get some methodologies with microwave data to add to the Dvorak. As we saw, we could get winds, and with some of the new microwave techniques, you could get winds through the whole range of the tropical cyclone. Also important is getting changes in intensification, not only up, but on the way down. In the old days, we used to forecast hurricanes or typhoons of, it's up to 80 knots, maybe it'll stay 80, or go steadily 70, 80, 90 knots. And now we need to know where it's going to peak. Say, 90 is as strong as it's probably going to get, at least for this period. We'd see the eye wall replacement cycle, or we know that there are other things that are affecting the tropical storm. And then we could start forecasting downward versus just keeping it one type of intensity. And of course, we could see all the items that you needed to do tropical cyclone analysis. I've showed this picture before. There's lots and lots of satellites, and you have to keep up on this. I've found out recently that if you don't read about them, you start getting behind in the technology. They just keep coming up. So that's what I'll try to do. And we just discussed, I see that David discussed this very quickly before, but here are some of the satellite sensors that fit under the active and passive. Interesting to me is the fact that passive satellites aren't as less usable than an active one, in that they're getting more and more sophisticated techniques to understand the winds and what you see below, besides just having active satellites. So I found this is very interesting. Active satellites send a pulse like a radar and get it back. Passive just receives the energy from what's below. And I've given some different summary of different types of satellites that we use on a regular basis. I noticed I put in altimetry. I don't know if we'll get to that talk or not later, but that's one of the ones that we've been using regularly and for the over the ocean. Synthetic Aperture Radar does high surveillance. And then the passive ones, like I said, are finding more and more tools on how to use it. It used to be only 85 gigahertz. 37 is what I used to use when I'm working at the Typhoon Warning Center and when I used to give techniques for, but now we have other types of satellite sensors that we can use. All are designed to fit in that big scheme. This is a repeat, but if you need to look at data, if you're an operational forecaster, you like to have it in the machine in front of you, but that's not always possible. So as I tell the people here at Weather Forecast Office Guam, if you don't have it on your weather computer, then go to the internet and look it up, because the data is important. So besides from the NRL page, which I have listed here, which is one of the first ones to give data available, there's also the NOAA CIRA, CIRA at Colorado State and SIMS at University of Wisconsin are both dedicated to providing new techniques, and they're also, many of them are integrated now with the Joint Typhoon Warning Center and the National Hurricane Center as well. So you could get some of the raw data, or if you're working at one of those offices, you get information sent right to you. As you can see, these are good. This is a good site, just like the FNOC site, in the sense that it will give you scatterometry data as well as the different kinds of microwave imagers. These are mostly the passive ones. The active ones we'll talk about a little bit later. Normally I use 85 gigahertz and the 37. However, there are even techniques for using the vertical and horizontal polarized data. The other site that I use regularly, and this is also being integrated into the National Weather Service, is the scatterometer pages that originally came from NOAA NESDIS, what they call the Manatee site. And this lets you pick and choose where you're looking at the data on a 24-hour basis. These are the ascending images, and then you would 12 hours later would be the descending. Of course, they're integrated so that at one side of the globe it's ascending, the other side of the globe it's descending. And then maybe people don't realize this, but they just like that other site at NOAA, at FNOC and NRL, where they specialize in a particular tropical storm when an invest is created. This one also gets triggered, what they call a storm folder that gets triggered whenever an invest is there, opened by either JTWC or NHC, and then you get more specific data for that particular site. Looks something like this, where you could get anywhere from just a blow up of the wind vectors to the ambiguities. The NRCS is something we talked about in earlier classes, normalized radar cross sections, which were very helpful. And then from BYU, and we're getting similar data from other agencies these days, is these high-res images where the actual direction is not as important as the intensities, and you could get a pattern from them. An example here is is here where you have an edge on scatterometer, where you could get the winds. And then even if these wind directions were wrong, and if you've used scatterometer, the chosen solutions are not always correct, you could at least get a very good impression about where the strongest winds are located, and then you get color tuned. Even here on Guam, we don't use this. I mean, we would use this for a typhoon if one was approaching, but we use, for instance, this yellow color as a way of telling us when we have a high surf coming or a small craft advisory, because it's just about right at our trigger level of 22 knots. So here, people in my office say, "Oh, we're putting out a small craft advisory because we're getting yellow winds." And that's what they're talking about. That normalized radar cross-section I've showed before, but in a way it looks like a microwave image, the way it reflects the wind, the surface ocean values, and it gets brighter as you get stronger winds, or even if it rains hard, which is sometimes a hindrance and sometimes an interesting fact that an eye might be an area where it's rain-free. The other site that we are using is what I call KNMI. I have this location here. And over the last year or two, I've been using what they've provided, kind of a request from me, of a multi-platform viewer, and I'll show that in a second. By the way, this is the 3 scatterometers that exist right now. See, I forgot to put the HY2 scat in there, so there's one more from the Chinese, the Ocean Scat from the Indians, and the CFO scat is a new one that's been up for a year or two, and they're still working on, because it has a new design feature that they are trying to see if this will work for future scatterometers. As you go to a KNMI site, you'll see many choices, and if you're not on the choice for a ASCAT A, B, or C, you might, or a SCATSAT, you might see on this side, if it's not open to this page, a multi-platform product viewer, and I've been using that quite often because it's very interesting that you could pick up, and I'm going to show one just from yesterday. You could pick up your choices of satellites over time over the same spot. You could almost get a time sequence of how winds have changed, and you also don't have to go from one satellite's page to the other. They're all kind of there at once. If where you click, by the way, is slightly off, they provided this northwest, east, or south type of movement, so you can just you'll move the screen, and then you get the image over the same spot. And recently they added ambiguity page, also because of a request, so that you could actually look at the ambiguities with the winds. His ambiguity display is not maybe as good as what we see from the other two NRL site or the Manatee, but at least they made an effort to try to make it user friendly. And then I should mention, look it up on my screen here, that the green underneath is the ECMWF modeled winds. There'll be types of data that we'll see that do not know the wind direction easily, and therefore, for the Europeans, the guide is through the ECMWF model. So we'll talk about that in a second. For in the US, they'll be using the GFS solutions. That also kind of gives you an idea how much the model, the scatterometer winds are being influenced by the model. Whether if you looked at a Manatee site and a KNMI site, you might see some different solutions. The solution is just one of the wind vectors. You might see some of the solutions flip because of which model they use to guide them. Now, scatterometer doesn't require completely model data, but when it becomes less certain, that's what they use as a guide. Now I'm going to change subjects a little bit and talk about antennas. And this is kind of on the basis of what David asked me to do, is talk about the SAR satellite. To do that, you need to know a little bit about how antennas work and how do you get the resolutions that you want. This is from the basic physics. If you want resolution to get better, meaning to see smaller, distinct objects, you got to do one of two things. You either have to make the antenna larger, and in space, you can only do so much, or you could look at the different. You could look at a smaller wavelength. The smaller the wavelength, the smaller the object can be seen. However, there on the bottom, I have the caveat: you have to do give and take, because in some cases, water and rain might affect the higher resolution data more than a larger wavelength. So you quite often have to work with different types of wavelengths, and that's what one of the things we'll talk about. But I just gave an example of going from a large wavelength to a smaller wavelength, or a smaller wavelength is a higher frequency. An example, 501 or 37 to 85 gigahertz is another. I just wanted to emphasize that I mentioned about the rain. Many of the scatterometer images, depending on the frequency, they're very affected by rain or moisture in the atmosphere, and they also tend to be difficult for some of the wavelengths at very high wind speeds or very low when there's no signal on the ocean. This is just a real quick summary again of rain can affect scatterometry data, wind data on the ocean. And this really is the case to some degree on any of these sensors trying to get ocean surface wind data, but they vary depending on what wavelength you're looking at. But the ocean roughness will be changed, and some of it's still unknown as far as wave turning and things like that. And then, of course, their absorption and scattering in the atmosphere. Another thing we wanted to talk about is, just as a summary, a quick reminder, is how as rain rates increase, different frequencies will be more affected. So that's why in 85 gigahertz, we see a very large, those colder temperatures that you saw on the bands, because they tend to scatter a lot easier than at 37 gigahertz and less and lower lower frequency. And same for both scattering and absorption. Both will take away the temperature that you see emanating from the ocean. Also, wavelengths change, as I mentioned. So the higher the frequency, the smaller the footprint, and then the more higher resolution, but it's a give and take. This is something I just wanted to show. I noticed David had a similar picture. It's just broken up a little bit more to show. Here's the SAR, the SAR band that I'm going to talk about later. The SAR satellite sensors are on here, the radar sat and Centennial 1 and 2. Also, we'll be talking about an L-band one, which surprisingly has shown up to be very of good value for getting strong winds. And by the way, this is where the ASCAT lies. And then the SCATSAT HY2 are at a higher frequency, which you would think would be good. It does see higher, smaller particles. It has a smaller footprint, but it is also more sensitive to rain. So it's a give and take between a Q band and the C band. Is everyone hearing me okay?
Yep, I'm hearing you good.
Okay. If there are any questions, just let me know. I'm learning some things as I did a background research on these data, and I wanted to know what really is a synthetic aperture radar. And it goes back to my resolution slide back a ways, where you might want to get higher resolution. You might want a bigger antenna, where you can only have so big of an antenna out in the space from a spacecraft. And so one way of doing it is another very sophisticated way is, of course, these things have multi-bursts at a particular frequency, and the frequency is fixed, but you could expand, apparently, synthetically, the antenna size by combining images. So here's an example where it would be doing multiple images over the same, multiple bursts at the same spot over the a multiple burst along the flight path over the same spot. And then synthetically, you put it together as a single image. Another way that that can be done is if you put a bunch of antennas on one satellite. But this is the way a synthetic aperture radar works. Also, you see many, when you go into the data, you see many data that has symbols of H and V, which you probably understand means horizontal or vertically polarized data. And as light hits different objects, it bounces back differently. And just to have a definition of how that works as a wave propagates in this direction, one may go horizontal. You can see the word transmit here, horizontal or vertical. And what that means is that our sensors are designed to pick up polarized imagery. This is especially so nowadays with the different advanced sensors. Some are called some look at data that's copolarized, where they transmit in horizontal and receive in horizontal, or vertical and vertical, or cross-polarized, where they might transmit in horizontal and come back vertical, or vice versa. And they found that whether you're in the ocean or looking at buildings or trees, the energy coming back is different and might explain exactly. From analyzing it, you could tell what kind of where the source of the data is coming from. So I hope that's somewhat clear. An example here would be from a SAR image. By the way, the SAR images, the raw images, are just like what I showed for the scatterometer. They're in what we call a normalized radar cross section, and you could see the width of each of the polar orbiting passes as they go through. But in this particular case, this one indicates a vertical transmitted and horizontal received, and then this is vertical and vertical. And they found that the resulting data is more influenced in one case by say a stronger wind, or from a different kind of rain value. And they're starting to understand more and more how these, what they call cross polarized images can be interpreted. Synthetic aperture radars, right now, there are a lot of these types of satellites, but the ones used for tropical storm imagery these days are coming from Sentinel 1 and 2, which were launched in 2014 by the European Space Agency, and EFRIMA, which is the French group, and then the radar set 2. This is an old satellite, but it's still being used. I didn't know Canadian Space Agency was this active, but alas, they are in partnership with other groups, including in this particular case, it's all private. The images, the sensors privately owned. And here are two sites that will show you data from both of these satellites, and they've got them all grouped up into different storms, which I'll show in a second. We'll go back here. I just wanted to summarize again. SAR data is not new. It's been available since the 70s. The images that you could see could show you whether it's buildings or terrain or underneath soil. There's many types of things that have been available, and then they're used at different frequencies. The ones that we're using for the meteorological, I think it's spelled wrong, is Sentinel 1 and 2 and radar sats. The scans are from a single sensor. So unlike scatterometry, which uses two different two different sensors from looking at two different directions from for a particular point. This is from the same semi-direction, but they use the co and cross polarization values to interpret the data. Direction, though, that needs to come either from an NWP model or a previous scatterometry pass or something that will tell them wind direction. The resolution, though, can be phenomenal in meters, and they have found that it works. Wind speeds up to 100, 140 to 170 knots have been detected. One thing in advance, and I'll kind of show this to you in the next slide, is that it's not running full blast on all the time. And these people that operate the sensors need to anticipate a location of a tropical storm and then be able to pre-turn it on at that time and then to analyze it. So it's not readily available just on a moment's notice. Even if the satellite did pass over the tropical storm, they have to have set it up to prepare at the highest resolution. Why? Because for Sentinel-1, they have different modes. You could see the different resolutions by looking at this thing, whether you could get by 5 by 5 meters at 80-kilometer whiffs, as you can see, is different whiffs, or here's 5 by 20, 100, 250 kilometers, or even more. So there's different modes that they have to switch on and prepare. And as you can see, the values we were just talking about, how things are the data is polarized, whether it's vertical, horizontal, retrieve. So all these things need to be anticipated. And here's some of the examples of things that they're looking at. Example. Now, I showed 2 sites on a slide before of where you could get data. This is NOAA NESDIS, but it comes from this Alaska demo site. And they happen to have, as you can see, also tropical cyclones, but just in case here, it's just showing how they were looking at winds. And you can see it's been around for a little bit of time. I could say winds off the Korean coast. Here's another example. By the way, you notice these are mostly in that normalized radar cross-section imagery, and they need to be further analyzed to get wind data. Here's one for a tropical cyclone, and they actually it says Halong. In this case, you could actually look up your storm of choice and see what is evaluated, and they all have a little bit of variance. So it's not exact values. They have to be trained. Since their imagery, they get trained by stronger winds from some other known source to say this type of brightness that reflects this kind of speed. This is from the other site that I mentioned that has this regularly available. It's called Cyclops. It's or IFREMA, and they have each of the satellites, each of the tropical storms documented with many of the different types of SAR, and in this case, SMAP and SAS. You could see that here's 3 SAR, and here's the SMAP and SMOS, which we'll talk about. But you can see how they're trying to intercept the different images as it goes through. And this is one of the ones that hit, but there's many choices. And then each of the paths you could actually click on within this site and look at how it's analyzed for wind intensities as it goes up. I believe this is in meters per second, not knots. So that's up at 120 knots. This is how a JTWC looks at there at one of these images when it gets sent back to them, thanks to Buck Sampson. He will send this over into their machines called the ATCF. You can see it as little data points that could be colorized to give them a view. For sure, you get a center. If there's cloud filled, this might be helpful. Otherwise, it might be obvious from other data, but it also gives you a touch of where the strongest winds may be found. And these are in excess of the scatterometer in many cases. And it will be Oh, close. It will help verify, for instance, the Dvorak technique, which we talked about before in another presentation. And then, of course, here's one from the Goni. Real quick, we'll go on to a different satellite. This is pretty interesting. Both the SMOS and the SMAP are failed satellite programs that have been found to be used for other information. They were both designed and in the L band, which we looked at, which is a large band, to look for soil moisture from an active sensor. Those failed, but the passive sensor that went with it is able to find wind speeds that are very strong. By the way, this site here, Remote Sensing Systems, is a very important. It is a site that I've been following for quite a while because they are one of the developers of scatterometry as well as other type of sensors. Frank Wentz has been in the program for over 30 years, I would assume. And he's got some top-notch guys working for him. And you could go to their site, and they've always had this kind of data where you could look up different tropical storms with different sensors. And you could see some of the sensors on the left there. And they also have them labeled by tropical cyclone. So it's Remote Sensing Systems, and that's their location. Here's an example of one of those SMOS images that JTWC has been able to get hold of, and you could see it gives similar type of data as we saw from the resolution is not as quite as good, but its ability at the L band not to be affected by rain allows it to see wind speeds that have been up in excess of 130 knots of wind, and of course you can detect a center with that. And so these are some of the schemes that are available to the Joint Typhoon Warning Center to get positions and wind radii. And that's always been one of the most important values, is not just max intensity, but the wind radii. And this can be used in league with the scatterometry. Maybe one passes over when the other doesn't, or something, or you can compare the two. Directions are not found with this kind of data, but you could get that from the model or just normal interpretation. This was a kind of a famous one that was advertised that when they were flying over Hurricane Patricia, one of the strongest tropical cyclones on record. They also had to have a path that showed winds over 70 meters per second, and that was the same time aircraft was verifying that kind of information. This is kind of a summary of what we're going to, and I'm going to still show some old information, old data, but I just wanted to say there's different scales over different times, and you need sensors with resolution and frequency to pick up this kind of any of this data. So here's just a kind of a summary page of what we're looking for from satellite sensors. WindSat is the one that we've showed before, but I found that it's more clever than I originally thought. How does a passive sensor get wind directions? Just like what we showed with these other higher resolution sensors. They've had this one since the early 1990s, and it uses different polarizations to get wind speed. And outside of rain, it's been very reliable. Another type of satellite that's been recently set up is trying to show how small, cheaper satellites might be able to help with wind speeds. It's another passive data. It uses 8 micro satellites that follow each other, and then it uses the energy from the ocean back to the GPS to them to detect wind speeds. And maybe it's been less used in the other data, but the concept is very interesting. As you can see, it could pick up a hurricane off of Florida, giving them an idea if you can't fly there, or if the satellite is not passed over recently. This might be another way to view the image, called the Cygnus winds. ASCAT. of course, I've already mentioned. I just wanted to show you the different orbital methods of how the sensors are picked up. In this particular case, this is an older technology, but it's used with pretty good results, having two paths. Each one is the same, but they look at a particular point as the satellite flies over the same spot at three different incident angles and three different azimuths, and then it's put together into a solution, which I will show quickly. That's compared to the old QuickScat, which is now also being used by the HY2 and by the SCATSat from India. It has a larger area. It uses a completely different way of combining two different images, two different sources of data from over the same spot. And then you get something like that, a normalized radar cross-section from one of the sensors, put it together to get the winds. How do they get the winds? This is just a quick reminder about accepting Bragg waves. Bragg waves are not ocean waves. They're the ripples on the ocean. And all the sensors we looked at are looking for this kind of roughness minus the SMAP. Anyway, if you use the multiple views, you get a kind of a solution that has to be determined mathematically to get what is the odds of receiving something at a different cross angle, and you get a probability solution. I wanted to show this because this is why there are ambiguities, is the solutions could be basically infinite. But if you put several views together or several micro polarized images together, this is the basis of how any of these solutions come about, is they get what they'd use a probability solution to get the maximum likelihood indication. And they're ranked as well. If this was ASCAT, they would mostly be just ranked ASCAT as 1 or 2 in 180-degree opposite directions. With the SCATSat and the HY2 and the old QuickScat, they came with more possibilities, which could be a plus or a minus, but also a little bit more difficult to interpret. Now, if you use ASCAT, where it's just 1 or 2, the solution actually may be in between like that. So you lose some of your possibilities. I've showed this before, but it's how you read an ambiguity chart, primarily from the circular orbits and the circular views versus the ASCAT views. With the ASCAT ambiguities, they're mostly up and down, although you'll see in cases there'll be third choices. With the new satellite sensor we have called the CFO SAT, it's been launched for a couple of years, but they're still having some questions about it. But it uses Q-band, which means it's rain affected. And one of the things they've changed is a fan beam, which gives it some more ability to see at different angles. And so that's the difference between a pencil beam and a fan beam. And it might be it's the basis of how they're going to want to use a new advanced scatterometer. It goes around the same as I mentioned, but it has a different ability to see at different angles rather than in a pencil point. So here's one of the new ones that will be launched in the next couple of years, where it uses both C-band and Q-band versus one or the other, because you can take advantage what we talked about, resolution versus rain effects. And so this is why I want to show this. This has ability to put both together, and that's exciting. Both bands working side by side. Here's the strategy. This is a nice reference page of what is up and what will come up in the future. Most of these have program monies involved already, but maybe you would see some as we go on with time. What the WMO wants is to have data every 6 hours. to help the NWP models. That doesn't always happen. And there are different reasons for picking orbital times, but you can see we still have some big gaps in imagery. I know here at Guam, we found that the QuickScat and even the ScatSat now is at a little earlier time, so it's available for easier for ours. This happens to be where our analysis is for the 0Z and 12Z data, while the ASCAT comes in a little bit later. So sometimes we kind of wish we had that data 2 or 3 hours earlier to do our analysis, but of course, any analysis is a good analysis. And you'll be able to get reference to this data later. This is some of the slides I've just shown come from these different sites, especially this Earth Data NASA remote sensing. I recommend strongly as a good tutorial on information. And that was my presentation for this particular slide. David, what would you like me to show, or have I run out of time?
Yeah, I think we need to give Moeka time to talk too. But that was great. That was a great presentation, and actually the first one where I will have to review it to make sure I caught everything that was in it.
There was a lot of things that I didn't want to show the same old stuff, even if you saw some familiar slides. But I think I personally learned a lot of new information about how sensors work.
Mm-hmm. Yeah, so did I. Yeah, so that's and for our Pacific Test students, if some of the information seems daunting, just focus on the fact that the SAR, what it does is it provides you with higher resolution of the winds and potentially the rain. Well, I don't know. We'll see in the future, but higher resolution of the winds so that you can see where those really, really, really fast winds are in the tropical cyclones. And then the spots where Roger told you that you could find the data. That's also the important part that you should take away from this. Yeah, but let's give Moeka time to speak on her topic.
Sorry, Moeka. ごめんなさい。
大丈夫です。Thank you so much. Yeah, can I share my screen? Can I start?
Yeah, you're a co-host, so you should be able to.
Okay.
Roger, did you release the share screen?
Yes.
Okay.
So, can you see my screen?
Yep.
Okay. So, my name is Moeka Yamaji from Japan Aerospace Exploration Agency, JAXA. So thank you today for this opportunity to sharing our satellite-based rainfall product for weather monitoring in Pacific Islands. So today, I will talk about a GPM mission and the Japanese GPM multi-satellite product called GSMAP. So first the overview and then algorithm, validation results, data access, applications, and summarize my talk lastly. So this is a very basic idea, but satellite rainfall observation allows us to capture the rainfall, even in the lack of ground-based observations. So we can measure rainfall from space globally and continuous and same interval and consistent accuracy. So GPM mission, Global Precipitation Measurement Mission, consists of the GPM Core Observatory, launched in February 2014, and other constellation satellites. The GPM Core Observatory here, GPM Core Observatory is like this. and is the only satellite in operation dedicated to the observations of precipitation from space, and has formed a focal point for precipitation research. The GPM are extremely capable of providing detailed observations of precipitation because their sensors include a combination of a passive radiometer and an active radar. This allows profile of precipitation characteristics from the radars combined with a global mapping capability of surface precipitation from the radiometers with wider observation worth. So NASA developed GPM microwave imager as a passive sensor, and Japan, we developed dual-frequency precipitation radar. We call it DPR as an active radar. DPR, dual-frequency precipitation radar developed in Japan consists of Ka band here, Ka band and Ku band precipitation radar, and launched in February 2014 from Tanegashima Space Center in Japan. So this is a kind of movie of introducing GPM mission. So here we can see the Typhoon Maria, and we successfully observed this typhoon from DPR, GPM DPR, and we can get the wider swath observation of precipitation by using passive imager and 3D structure of precipitation by using dual frequency precipitation radar. And we also have other constellation satellites, so we can get this kind of passive passive microwave radiometers like this, and we merged this kind of data set and generate the multi-satellite product called GSMAP. So this slide shows the features of each of sensors. The first one is infrared imager like Himawari Ahi, and second one is microwave radiometer like both imagers and sounders. And third one is precipitation radar like GPM, dual frequency precipitation radar. So infrared imager measure cloud top temperature, and it can't directly observe precipitation, but we can use the relationship between the cloud's height and the rainfall intensity. So if low clouds may have less rainfall compared with high clouds with heavy rainfall. And next one is microwave radiometers like GPM, GMI. So it measures intensity of microwave radiation that is constantly emitted from raindrops here. And it can estimate spatial distributions of precipitation with wider swaths. There are many microwave radiometers in operation. So we can use multi-microwave radiometers for GSMAP. And last one is precipitation radar. This can actively emit pulse and measure the echoes reflected back from drops here. So precipitation radar can detect vertical distributions of precipitation, but the source is relatively narrow. So, but there is only one precipitation radar in operation over the world developed by us. So this is very essential information for our GSMAP algorithm. This is a product of GPM, dual frequency precipitation radar. As you can see, we can get the three-dimensional structure of precipitation like this. And this is the case of Cyclone Winston in 2016, which attacked Fiji and many thousand Pacific islands. So we can also detect the latent heating and diameter and precipitation phase information. So this kind of unique information can be obtained by using GPM DPR. So we mainly use GPM core observatory, and we use dual-frequency precipitation radar, and also we have GPM microwave imager on the same platform. So dual-frequency precipitation radar can provide reference standard to GPM microwave imager. So we calibrate these other constellation satellites by using GPM microwave imager. And we also use geostationary satellites, IR imagers. So we generate this kind of global precipitation mapping called GS map. We distribute this information to the public. This is a movie of GS map. I hope you can see this movie, but left-hand side is Cyclone Harold in April 2020, and right-hand side shows Hurricane Douglas in July 2020. As you can see, the Hurricane Douglas moved from the Eastern Ocean and goes past through the north side from Hawaii here. So this shows the user information of GS map. So there are many Asian and Oceanian users. For left-hand side, for downloading data, quick registration is required for the users. So many Asian users analyze the GS map dataset for various purposes. So as of October 2020, we have about 6,700 registered users from 136 countries. And for monitoring real-time rainfall, websites are useful too. Users can use a website without registration, so that many users from Pacific Islands use it for real-time rainfall monitoring. This is very easy to look at global rainfall, so I hope this can help your operational utilizations. So we use precipitation radar, microwave radiometer, and infrared imager. So how can these different sensors be used in the GS map algorithm? So next, I'll explain algorithm to generate GS map. So this shows overview of GS map algorithm. At first, each precipitation is estimated by dataset of microwave imager and sounder using rainfall database of precipitation radar. So firstly, observed information by microwave imager and sounder is converted to the rainfall rate by using rainfall database from this precipitation radar. So we can get rainfall data from each microwave radiometers. So as you can see, the left-hand side is a microwave imager from GCOMW AMSA2, and right-hand side shows a microwave sounder from NOAA 19 AMS-A MHS. So depending on the type of microwave radiometer, precipitation intensity and resolution slightly differ, like this. So secondly, rainfall data from each microwave radiometer are merged. So we consider the X-calibration and merge microwave rainfall data like this. But some area cannot be covered with merged microwave radiometer data in 1 hour. So then rainfall in no covered area is estimated by IR imager on geostationary satellite using microwave IR merged algorithm. So I'll show you that microwave IR merged algorithm. So at first, cloud motion vectors is calculated by 1 hour before IR data and present IR on geostationary satellite cloud motion vector. And second, 1 hour before GS map is propagated by the motion vectors, and the predicted GS map is corrected by using Kalman filter here. And finally, this predicted and corrected GS map is overwritten by present microwave retrieval over processes. The product created by such a process are called as GS map NRT or GS map MVK. Finally, I'm going to explain gauge adjustment algorithm. So GS map MVK here is corrected using NOAA CPC global daily gauge on a daily basis. Yes. And next, GS map NRT is optimized using the GS map gauge. A product created by a such kind of process is called a GS map gauge NRT. So some a little bit very complicated, and we have some kind of GS map products like GS map standard version, GS map near real-time version with 4-hour latency, and GS map real-time version on quasi real-time and updated every 30 minutes. So you can choose which GS map to use for your purposes. For example, for long-term analysis for climate or agricultural monitoring, GS map standard version is maybe useful for users. But for flood analysis and weather real-time monitoring, latency is very important. So you can use GS map near real-time version or GS map real-time version. Noted that GS map MVK and GS map NRT has past duration available since March 2000. So you can get the dataset for more than 20 years. So this is a detailed table for GS map product. Standard version, near real-time version, and real-time version. And without gauge adjustment and with gauge adjustment. The domain is global and resolution is 0.1 degree latitude longitude and hourly rainfall. An update interval is basically hourly, but 30 minutes only for real-time GS map. And next I'll show you some validation results of GS map over Japan. So this slide shows a comparison between each GS map product, and here is a JMA's radar Amedas, which is gauge calibrated radar analysis. And here is NOAA hydro estimator, well-known real-time rainfall product. But hydro estimator is based on the IR imager, not the passive microwave and precipitation radars. So as you can see, accuracy over Japan is highest in gauge-adjusted version. Correlation is 0.72 and root mean square is 0.229 millimeter per hour for daily accumulation basis. And then GS map standard version, NRT, and now. But GS map now has correlation of 0.63 and root mean square error of 0.33 millimeter per hour, which is still higher than hydro estimator. And this slide shows the seasonal variation of GS map accuracy. Is April, June, August, October, December, February, April, June, like this. And vertical axis shows spatial correlation. And color indicates each GS map product. So accuracy varies seasonally around Japan, so which suggested that the accuracy depends on some factors like precipitation amount and characteristics. And same kind of validation analysis in Japan using JMA radar gauge analyzed data and GSMAP NRT was conducted in some resolutions. So the accuracy got better as the spatial temporal resolution became coarser, which is because shift of location and time is cancelled. So as you can see, root mean scalar table, 1 hour hourly and 0.1 degree root mean scalar is the 1.20, but daily accumulated rainfall in 1.0 degree latitude longitude, it got better as 0.35. So if accumulating 3 months of rainfall, the GSMAP is almost same as ground-based dataset. And if taking spatial averaging as 0.3 degree, 0.5 degree, 0.8 degree, the accuracy got better as the spatial resolution get closer. So next, I'll show you data access, how to use GSMAP. So we prepared some websites for checking GSMAP rainfall distributions. For users who would like to monitor precipitation in real time, you can use JAXA Real-Time Rainfall Watch. You can see global precipitation map updated every 30 minutes. And for users who would like to see precipitation in the past specific date, JAXA Global Rainfall Watch is useful. Users can see hourly global precipitation map since March 2000. And for users who would like to see daily or monthly precipitation, JAXA Climate Rainfall Watch is useful. And you can see indices related to the extreme heavy rainfall and drought, as well as accumulated precipitation. So here you can change the date from here, and you can see the product name here. And country search and location change functions are installed in the GUI of GSMAP website. And you can overlay geographic layers that like coastal line, latitude, longitude, graded, and the river. And you can check accumulated precipitation as 12 hours, 24 hours, and 72 hours from these buttons. And as I mentioned earlier, GSMAP is generated by using both passive microwave radiometers and estimated rainfall by using IR information. So you can identify by using this button and overlay cloud and or information from here. And if you double click here, you can check the value of the grid, and you can download the image from this function. And also subset the data set and download the data by the format of CSV format. And if you'd like to analyze our data set, you can download the data after your registration. This is free of charge. So if you register from the website, FTP server information will be sent via email. And the specifications are explained in the documents. So if you're interested in this kind of data set, please visit our website. And lastly, I'll show you some examples of applications, especially over the Pacific Islands. So this shows the utilization in Pacific Islands. So I visited these islands, all of these islands, and explain what is GS map, and please use this kind of GS map dataset for promotion. So GS map has been used for rainfall monitoring by meteorological services in Pacific Islands like this. And some agencies from like Fiji Meteorological Service, Coast Coast, Samoa Meteorological Division, and Solomon Meteorological Service Division, they put the link to the GSMAP website from their own official website. So it's easy to visit our website via their own official website. And this shows a combination of Himawari and GSMAP. So here is a photo of forecaster in Solomon Met service, and he used both Himawari information and GSMAP information. Cloud information by Himawari has high resolution, both spatial and temporal cloud information, and precipitation information by GSMAP having hourly 0.1 degree resolution, which is coarser than Himawari IR information, but based on directly observed precipitation information. So cloud information by Himawari provides essential information to monitor the locations of precipitation systems moving by minutes. In addition to the fine resolution cloud information, GSMAP can provide the rainfall information, which is important for the quantitative rainfall monitoring. So it's difficult to identify where the heavy rainfall area is within the typhoon, but tropical cyclones do not always have a symmetrical precipitation structures like this. So rainfall information is very important for monitoring typhoon. And we have wide range of utilization fields. So for tourist information in regards to storm rainfall in Chuk Visitors Bureau, or determining better schedule to conduct outside or field work so that their equipment not damaged from the rainwater by coastal resource management, and analyze the disaster in the viewpoint of climate change. So here is provided by our colleagues from Solomon Island. So they use GSMAP to plan and respond to areas where rain rate was considerable high. And Samoa Met Services uses GSMAP to post the rainfall status to the Facebook. And this slide shows climatological applications. We started to operate a website, JAXA Climate Rainfall Watch, which provides information about extreme heavy rainfall and drought over the world based on GSMAP statistics. So left-hand side shows a drought in Australia, December 2019, and right-hand side shows the area 90th percentile during Harold April's 3 to 9, 2020. So these website can display accumulated rainfall in some temporal scale, daily, pentat, weekly, 10 days, and monthly, as well as 20-year climate normal and indices like heavy rainfall and drought. And this is last slide before summary. So we planned GPM Asia Oceania workshop in March 2020. The 8th GPM Asia Oceania workshop on satellite precipitation data utilization would be held with PAGASA, Philippine Atmospheric Geophysical and Astronomical Services Administration in Manila, Philippines in March 2020. That it was postponed due to the COVID-19 pandemic. Until 7th workshop, the name was GPM Asia Workshop, but renamed to GPM Asia Oceania Workshop and invited some Pacific agencies such as Guam, Australia, PNG Met, Fiji Met, and so on. So if you're interested in the workshop, please contact me. I will invite you, maybe, yes. So let me summarize my talk. So as one of the Japanese GPM products, GES map has been developed and widely used in various purposes. GES map is a multi-satellite product by using passive microwave radiometers, IR images, and precipitation radars. GES map is used in Pacific Islands for monitoring real-time rainfall distributions in large-scale viewpoint. The data can be quickly checked using websites and also be downloaded via FTP site. So if you're interested in GSMAP, please visit our website or contact me. Yes, so that's all. Thank you very much.
All right. Thank you, Moeka. I particularly like the point that you made about the Pacific Islands offices, including a link, because this product, like the real-time product, it's pretty intuitive, like a normal radar. So the general public can use this pretty easily too, as well as it being a forecast tool.
Yes, thank you so much. Yeah, so if there are some agencies who would like to put the link, please contact us. We will prepare for the website dedicated for the island.
Oh, okay. Like a high resolution.
Yeah, or change the time to the local information.
Okay.
Yes.
Okay, so does anybody have any questions? I didn't see in the message. Thank you, Roger, for a comprehensive overview. Does these data get into the E-Trap product? I think that's for you, Moeka.
For me?
Trap? Have you heard of that?
Yeah.
Yeah, I asked that question. We get data from NOAA and NESDIS on tropical cyclone rainfall, and it seems to me maybe they use your algorithms or your data. Do you have contact with them? It's one of the ways we forecast rainfall for approaching tropical cyclones.
Do you mean the this data exchange, or?
Well, there's a real-time product. I don't know, maybe Scott Lindstrom, I see he's in this list here. Maybe he knows.
So GSMAP information is used for the typhoon monitoring or something?
Yes, and one of the products is called E-Trap.
Yeah, I'm not sure how GSMAP is used for the typhoon monitoring, but in Asian case, many agencies use GSMAP for typhoon monitoring, also for Pacific Islands. But yeah, I'm not sure in case for the US side. But we work closely with NASA, and NASA also has this kind of multi-satellite precipitation product called IMARS. But IMARS doesn't have the real-time version. So for operational utilizations, GSMAP may be useful for the users. Can I answer to?
I haven't looked at IMARS before, but I assume it's not. Your guys' product is particularly useful to our audience because you're centered over Japan, so you're you are focused on the South Pacific and Micronesian regions. I'm not, is IMARS, does it just cover near the United States or?
Yes, IMARS may be, yeah, more useful for the research purposes. I think so.
Roger Scott said that he doesn't have any.
I read his, I read his thing on the chat. Could I ask one more question?
Sure.
The algorithms that for picking up rainfall, did they change with rain systems? Or I saw your accuracy for just Japan, but the rainfall amounts that you get from a tropical cyclone must be different than, say, rain over Japan in the wintertime, right? How does that
Yes.
change?
So, so we use this kind of lookup table method by using precipitation radar. So precipitation radar provides global scale rainfall, three-dimensional rainfall information. So we can use the regime database and kind of radar rainfall profiles by using precipitation radar, and detailed information of precipitation is used for the retrieval algorithm of microwave imagers and sounders. So the climatological differences of the precipitation and its seasonal changes is taken into consideration in our GSMAP algorithm.
Well, thank you very much.
Thank you.
Okay, I think this question is for Roger. Is SAROPS mainly for the Northern Hemisphere, or does it also cover Southern Hemisphere?
No, the SAR is global. Is global. In fact, one of the ones I showed was for the South Indian Ocean. So they, the only thing that I was not positive about is the request to get the SAR open for a tropical cyclone. It seems to me that the radar sat people Canadian might be more vested in hurricane Atlantic, but I'm actually not sure. But I think at this point, any major storm, I think it's good for the data. So I was given some locations where you could request in advance. I think I'll leave that to the researchers in Wisconsin and Colorado State and JPL NASA guys to make those requests. But the data is global.
And then for Moeka, can the GSMAP data be displayed on SAT-aid software, perhaps an overlay with the Himawari 8 data?
Yes, we strongly hope this kind of collaboration with JMA, and we're discussing whether GSMAP data can be distributed via the Himawari cast or something, but still under discussing. Can I, thank you for the comments. I will, feed back to JMA colleagues these comments. Thank you so much.
Okay. So Ginger, were there any comments on the Facebook side?
Yeah, that was, you had asked that question from Facebook.
Okay. 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 I think that's, unless our presenters have some final words they'd like to share with us, then I think that we'll wrap it up for today. There's a lot of information there. If it's okay with both of you, I'll be able to get your presentation slides so I can pass those on.
Okay.
Okay. You have mine already.
Okay. Okay, great. So in the next coming days, I'll be writing up a recap on the website, and I'll post the links to YouTube. This should go right up automatically on Facebook, I think, afterwards as a video you can rewatch. And then I'll I'll also put the slides on the Facebook page. Yeah. So yeah, thank you again, Moeka and Roger. Those are really interesting talks, even for me. A lot of new information that I wasn't aware of in those.
Thank you for the invitation. Appreciate it.
Yeah, you're welcome.
Thank you so much.
Okay, so then I hope I get some interest in people who want to present, just do a virtual tour of their offices. I think that would be a fun way to wrap it up for this season. And maybe do that beginning, middle of December, sometime not too close to Christmas. And that'll be it for this year. Okay, so thank you for joining us. See you soon.
Thank you.